Hi, I, Rostislav Zinko, will introduce you to building your first application with Go video course and take you through all the sections. This video course is an introduction to the Go language that aims to give you a strong basis of application development. So, by the end of this course, you will be able to design and create your own applications in the Go programming language. The first thing we have to do before starting development is bootstrapping the workspace. In order to get things to work, we will need to accomplish the next three steps: downloading the project, installing the project, and setting up the development environment. So let's start with the first one. Google Go is a compiled programming language. A compiler is a piece of software that translates your source code written in the Go language into the machine code, which your machine is able to process. That's why getting a compiler would be our first step, which is mandatory. First of all, you need to visit the official website of the Go language, http://golang.org, which will guide you to the web page from where the download is available for your platform. We will download the Windows version, but if you have another operating system, you will have to download appropriate binaries for you. Actually, we're going to download the binary distribution of a compiler. It means that the compiler is ready to use. On the other hand, Go compiler is an open source software, so you can compile it yourself from the source code. The latter is good if you would like to hack the compiler or for those who would like to try the newest things immediately. You can follow the project tab at the golang.org page in order to get instructions. If you are using the macOS or Windows operating system, you can download the pkg or MSI installer files and simply run them. However, if you are a Linux or a FreeBSD user, you will have to download the tar.gz archive and unpack all the files into the folder where you would like the Go programming language compiler to reside. After you have performed the previous steps for your platform, you should have received an installed binary distribution so that you can write Go in the command line and you should see the help. The executable for the Go tool resides in the bin folder of the distribution, and you have to add this folder to the path environment variable manually in order to run the Go command without specifying the full path to the executable. The path variable is also important for the Windows OS, but it is set automatically if you use the binary distribution. If you see the help, congratulations! If not, redo the previous steps and check if anything was missed. Having a working compiler is reaching halfway to success in our first task. Another thing that we need to do is to choose a folder for our future workspace. I will create the Go folder on the disk D. Go workspace is represented by a folder that contains three subfolders: bin for storing compiled binaries inside, pkg for storing compiled package object files, and src for storing applications and the package source code. So let's go ahead and create these subfolders. Actually, only the src folder has to be created manually. The other two are created automatically. Go compiler, while building your application, uses two places to find the source code and compiled packages: its standard library and your workspace, which you can use to store the code for your applications. The first is denoted by the Go root environment variable, which is set automatically, and the second is denoted by the Go path environment variable. The Go path variable must be set to a path to the folder where the workspace is located. This approach is actually very convenient if you have different workspaces for different projects on a single machine. By setting the Go path variable, you can seamlessly switch between workspaces, though it is a common practice to keep several projects in one workspace. To check if everything was done right, you can type goenv in the command prompt, which prints names and values of environment variables that the Go compiler uses for its needs. If you find Go root and Go path with their values accordingly, congratulations! The workspace was set up successfully. At this point, you have your Go language compiler installed and your workspace set up. And now we're going to move on to the next topic to compile and run our first classical Hello World application. A little note about the text editor. I will use Sublime Text 3 throughout the course, which is free and can be downloaded at www.sublimetext.com/3. In the previous video, we managed to download and install the Go compiler and set up the workspace in order to be able to build applications in Google Go. This video will show you how to build your first application. Getting the very first application to work is very significant, as it will show you the overall workflow of developing the Go application from scratch. starting from writing a simple Go program, compiling it into an executable, and finally run that executable. Every Go application consists of one or more packages that are the largest reusable building blocks for every application. Packages are compiled into separate object files, which are then gathered and linked by the Go compiler into one big executable. Go supports only static linking for now, and that's the reason why final executable is quite big compared to similar applications written in C, for example. The one mandatory package that must be present in every application is the main package, which contains the entry point for your application. You can also import other packages that implement certain functionality for you, and we will cover this in the near future. Actually, you will use packages all over time because you can make use of a library by referring to its package. For our first application, we will use only one package called FMT that implements text formatting and output to your command line interface. Every executable must have entry point and instruction for the processor to be processed first. Go language defines such entry points through the function main, and the execution of the application starts at the first line of this function's body, surrounded by curly braces. So, as we have the main function defined, we are ready to fill in the body. The aim of the first application is quite simple. It just displays "Hello World" onto the screen. We will write it in English, but you are free to experiment and use your own language, as Google Go demands that the source code must be UTF-8 encoded. Here we have some more advanced concepts, which we will discuss in future, but will explain a bit now. Here we call the println function, which displays text on the screen by adding a new line at the end of the string. Before the function name, we see FMT and dot. That tells us the function is taken from the FMT package. It is located in the standard library and is distributed along with the compiler. Braces denote the function call and the string is the parameter. As we have finished defining our source code, we are going to save it as the code.1.1.go file inside the code.1.1 folder, which resides in the src folder. Compile it and run. Usually, you have to compile and link the code into an executable format and then run it. But the developers of the Go language squashed these steps into the build step. Also, Go makes a strong emphasis on compilation time, which can get 10 times faster than C++, for example. For this, being inside the root folder of our workspace, we type go run src /code.1.1/code.1.1.go and we see the hello world string printed on the screen. For the first run, it can take time for the compiler to get heated up compiling all the dependencies, which may be not that obvious for now, but all the forthcoming runs will be much faster. For a middle-sized project, it takes only a few couple of seconds to run an application, which is very good for a compiled language. At this point, you have written, compiled and run your first application in Google's Go language, which is a great result in such a short time. Though we were successful in seeing the very first results, the Go run is not always the way out. Running application that way is convenient for faster testing and checking results for small applications, but is not very suitable for larger projects having disk input-output or other outer dependencies. And the temporary executable that is created and removed by the go run command as the application finishes does not fit the needs anymore. So, we're going to move on and get familiarized with some other powerful and useful features that the Go tool introduces in the next topic. In the previous video, we managed to write and run our very first application in the Go language, and we used the go run command to build and run the final executable. As it was said earlier, go run removes the executable immediately as the application finishes. This is why the Go tool presents other tools for building applications. While this topic offers you a pause in code writing, mastering the Go tool is essential as it will help you work efficiently with the source code, including ways to solve tasks such as compilation and linking, code formatting, documentation generation, and running automated test suites. To get information about the possibilities that the Go tool offers, you can type Go help in the command prompt. This will print a list of available commands. Or Go command name help to get a short documentation on a specific command, as you can see based on Go help env. So far, we are familiar with two commands provided by the Go tool, go env and go run. While go env helps us get information about the operating system environment that is used by the tool, go run allows us to implicitly compile the source code and run our application. So, let's continue on the building topic and start with go build. It is the most general way to build applications and separate packages with Go. You can either provide the name of the package, in our case code.1.1, or a path to the Go source file, in our case src/code.1.1/code.1.1.go, and the Go tool is smart enough to decide what to build. The result of this step is an executable that resides in a folder from which we called the tool. But you may have possibly mentioned that your workspace also has the bin folder, which, as we said, must contain binaries. Yes, that's true. In the name of order, we can build our application to the bin folder using the -o modifier, telling what the path of the final executable should be, as demonstrated on screen. You can also read about the command modifiers and their functions by typing go help build. Let's move on. While Go build is powerful enough, it's not very convenient for large projects having third-party packages as dependencies, and this is the case where Go install serves as a nice shortcut. It basically does the same functions as Go build does, but installs final executable to the bin path by default and also builds all the needed dependencies. Here you can watch the result of Go install on the screen based on our Hello World application. The build executable resides inside the bin folder of the workspace. More information on the go install command can be found by typing go help install, just as we did with other commands. Another useful thing that the Go tool can do is code formatting. Usually, code formatting is done by IDEs, but in case of Go, there's a standard and GoFMT does its job well. Let's run GoFMT on our source and see the results. While software developers can be very disciplined in source code formatting, people are likely to make mistakes, and it is worth running GoFMT on your source, especially before you commit changes to the source control system, such as SVN or Git, in order to simplify reading your changes to your teammates. And last but not the least feature of the Go tool is a test running function. Go supports automated testing out the box, and the Go tool is used to run these tests in an automated way. The go test package name command scans your source files for those whose names include the _test suffix and looks for test cases executing them in an isolated environment. Let's try to test our application. As you can see on the screen, the tool ran successfully, though no test files were found. We will cover testing in future to show their significance in the software development process. During this task, we have covered the most significant aspects that you need to know to start developing in Go and feel convenient all over the software development process workflow. We saw how the Go tool can be efficiently used to format your source, build executables, and run automated tests for your application. Using this knowledge, we are moving forward towards writing our first useful application. We have devoted the last topic to studying the possibilities that the standard Go tool offers in order to simplify the overall flow of application development in the Go language. And now it's time to write our first application that may be somehow useful for the end user. We are going to see how the information flows through the application being processed and deliver some value to the end user. The application we wrote before basically did an output of the text, while the essential purpose of every software is to pass the following three steps: receiving data, processing data, and delivering the result of the data processing. So let us write a simple mathematical application that calculates the length of the circle by its given radius, which can be useful in the graphic or geographical application. The first thing we have to do is something you already know how to do, so we won't start with a blank text document but will use our Hello World application as a basis. Let's remove the main function body to start coding the current task. First of all, we need to process the user input. It's actually how we take the radius value from the user. The easiest way is to use the standard input from the keyboard, and the well-known FMT package will help us with it. The first challenge is how to store the value in an application. This is what variables can be used for. Go is a statically typed language, so let's define a variable radius of float32 which holds a 32-bit floating point value as shown on the screen. Variable is an entity that has a name, which is called identifier, and a value stored in the main memory of your machine and bound to that identifier. Identifier is used by the developer to access the stored value. The word variable tells us that this value can change during the time the application works. The next step is taking a value from keyboard and saving it to the variable we have declared. And here the fmt.scanf function is the way out. It takes two parameters: template that shows what type of data will come from the user. Also, the template syntax can be found in the documentation at golang.org in the Packages tab, and variable to store it. While some syntax can be unfamiliar for you, for example the ampersand, you don't have to worry, we will cover it in detail in the future. Now you can use GoRun to try this piece of code, and you will see that the program has stopped waiting for you to enter the circle radius. Let's enter some number and see how the execution stops. Let's move on. Now, when we have all the initial data to work with inside the application's memory, we can start processing it. Let us make another variable of the same type to hold the result of our calculations. Let's call it length. The formula for getting length is pretty simple. 2 multiplied by the p constant multiplied by the circle radius. Let's code it. Here we assign the result of the formula to the newly declared variable length. And as you can see, Google Go works with mathematical operations having syntax similar to what mathematicians use and supporting well-known arithmetic operations. So, as we receive the result in our application's memory, we are ready to show it to the user on the screen. Let's use the println function we're already familiar with and print the result of the calculation on screen. As you can see, we'll pass two arguments here, and you're actually free to pass any number of values you would like to display in a row to this function. Let's run the application with GoRun from the workspace root folder as we did previously with our very first application and see the result. For a given radius of 1, we receive 6.28 as the length of the circle. Congratulations! By accomplishing the task of writing this small application, we've done something useful in Go so far. These tasks showed you how a typical information workflow is organized in Go applications as an example of standard input. Of course, the application can take information from other different sources, such as network or hard disk or some other device connected to your computer. But standard input stream will be very useful during our course as it is the simplest way to test if your application works. And now let's move to the last video of the first section that will introduce you to the ways of Go code commenting. The previous section provided you the first useful application, and you've encountered some new syntax and concepts you didn't know before. New things like variables, new function like scanf, and new syntax element like ampersand, which I intentionally skipped explaining, were also introduced, and I've explained each row of code for you. I suppose it is pretty simple to understand the code using explanations as I do, but developing software is often held by teams which members cannot spend their time on voice communications, so they use comments to explain key things, especially over large and complex code base. Let's move on to see how you can help your team or yourself reading your code days or weeks after writing by using comments. Go offers two types of comments, multi-line comments and single-line comments. Let's start with the first one. Multi-line comments begin with slash and asterisk symbols and end with asterisks and slash symbols. They are useful when you want to write in place documentation or rich description of some code block. Let's comment our main function with a multi-line comment as it contains all the logic of our application. This explanation is pretty rich and gives an understanding of what the function does to the reader. Also, multi-line comments can be used to write documentation generated by the Go.doc tool. But first, let us cover another type of comments, single-line comments. Single-line comments start with two slashes and go to the end of the row. They don't require trailing symbols marking the end of the comment. Let's add some comments to give a full understanding of the source. Much better, I suppose. Now the source is pretty descriptive in itself. Of course, you don't need to comment every code line, but it is useful to leave some tips for others when you are writing complex applications. Also, single-line comments are useful to place marks across the code like to do, which are understood by most of the IDEs. And the last useful feature of comments is that they can be used to generate documentation in different formats for your application or package. Almost all developers of Go packages and the language itself use the Go.doc tool to generate documentation on their products. Let's try it on our project by typing Go.doc code.1.5 and see the results. By default, the result is in plain text and is printed on the screen. You can check the documentation on the Go.doc comment at Go's official website and play with parameters and ways to document your code. You will find this way of documenting powerful enough in most cases and for almost all software you're going to develop. It may not be obvious now why commenting is significant, but as applications grow while developing, it becomes increasingly difficult to remember what certain piece of code does. At least it takes time to review the code and get in it. It is especially difficult to read code written by other people, so commenting will help save you a lot of time. With these words, we finish our first section and it's time to review what was done. We've installed and got a working workspace for Go language projects. We wrote our first useful application. We also played with the Go tool and got familiarized with its main possibilities. And finally, we commented our first application in order to simplify its reading by other people. So far so good. Now, we are ready to move to the next section in which we will be learning about the Go type system, including basic and complex data types and everything about how data can be organized in the main memory inside the Go application. Let's continue our building your first application with Go video course by opening the next section called Basic and Complex Data Types. The previous section of the course was mainly devoted to studying the possibilities of the compiler and tools that are provided out of the box and the basics of writing Go applications, mainly the typical application structure and the standard input-output. Let's start with the first task of the current section called Variables and Constants, which we partly got familiarized with earlier. Getting knowledge on variables is essential for every programming language that supports imperative paradigm, one of which is Go itself, because they provide access to the main memory of your device via your application. So, variable is basically an identifier and a correspondent in memory storage which you can get access to via that identifier. Go is a statically typed language, so you have to set a variable type explicitly or implicitly. Such automatic deduction of a variable type is called type inference. Variables can have different scopes. This means that they are accessible from certain parts of the code and are inaccessible from others. The first place to declare your variables is the package level. If you declare your variables on the package level, They can be used from every module and function inside this package. Let's see how. The variable declaration syntax consists of the var keyword, identifier, and the type name. An identifier is a sequence of one or more letters and digits. The first character in an identifier must be a letter. Identifiers are case-sensitive. The underscore symbol itself is a special identifier called the blank identifier. It can be used in declarations of or variable assignments like any other identifier, and any type can be assigned to it, but its value is discarded, so it cannot be used anymore in the code that follows. So let's see how it looks like on screen in an int variable example. The int type means that your variable will hold the integer number, and the size depends on your hardware architecture, for example a 32-bit module chunk for the 32-bit architecture. The name variable means that the variable can hold different values during its lifetime, but values themselves are restricted to the given type. You can assign values to variables anytime you want by using the equality sign, which is an assignment operator in Go. It often happens that you might want to declare more than one variable at a time, and actually even tens of variables usually, and Go offers the var block syntax for that, so you are free of repeating the var keyword for every variable. Let me show you how it looks like by declaring two more variables, one of the string type and one of the int64 type. As you would have possibly guessed, int64 means that we would like to use the 64-bit storage for our integer number. Another type of storage that Go provides are called constants, which are declared like variables but with the const keyword. Their nature is pretty similar to what variables are, with one exception: values are assigned to them only once and cannot be changed during runtime. Constants can be character, string, boolean, or numeric values. Let's declare a constant with certain value, for example the mathematical p number, and we will also add the equality sign here and try to change it in the main function body. Let's run our application to see what we will receive. As you can see, the application cannot be run, and the compiler tells us about this with a message. Similar to variables, constants can be organized into blocks by embracing declarations into round braces after the const keyword. Also, it is not required to put the type of the variable or constant explicitly if you use an initial value for them. The compiler is clever enough to define a variable or constant type with the given value. So, we are done with package-level variables and constants. However, the same can be done inside a function. The syntax is the same except that your variable will live only during the function execution, while the package-level variables live all the time the application lives. Go is a garbage-collected language, and in Go it means you need to explicitly allocate memory for variables when first declaring them, but you don't have to bother on deallocating the memory. The Go language runtime manager does it for you. Also, you can use short assignment statements consisting of the colon and equality sign here. This way, you can explicitly declare variables and assign them results of the function calls and expressions without declaring the explicit type. Let's code a simple mathematical formula to illustrate this and run it to see the results on the screen. It's often handy to declare variables inside a function if you don't need them anymore across application, and it also frees memory from time to time, which makes it more memory efficient. If you use a short assignment operator inside a function, the type is inferred by the Go language runtime automatically. And the last thing you have to know about the scopes, you must be careful with them. Consider a situation where you have two variables of the same name. The first is declared at package level and the second is declared inside the function body. When you're working with the function, you're working with the variable you declared inside this function, called local variable. However, while working with another function, you'll access a variable at the package level, called global variable, and you must track that to avoid confusion and semantic mistakes. Up to this point, you have been able to declare constants and variables of simple type and understand the scopes of the variables and their lifetime. Next, we are going to discuss Go's simple standard data types and what operations you can perform with them. The previous video of this section was devoted to the discussion of the variable declaration syntax, which is essential information about how to store data in the main memory of the application. Also, it is worth mentioning that Go has a set of standard data types that are ready for use, and we are going to learn them during the next tasks. All data types in any programming language can be divided into two parts, basic and complex or scalar and vector types. Let's start with basic ones, as they can be used to store the simplest pieces of data and for building more complex data structures. The first and the simplest type is a Boolean type denoted by bool. This data type can hold only two values, true and false, and is used to denote the result of a logical operation. For example, showing if one numeric value is greater than another. Let's define two Boolean variables and print them out with the println function. We'll also show you operations on Boolean at the end of this video. The next set of types are numeric types that are used either to store integer numbers or floating point numbers, and we've been working with them so far. Go offers two floating point data types, float32 and float64, and numeric parts of these types' names denote how many bits of memory this data type can store. Let's define one floating point variable in our source. There are also complex 64 and complex 128 data types for storing complex numbers, but we won't stop at them as they are specific to mathematics and are rarely used in application development. And the second set of numeric data types is used to hold integer numbers, either signed, that allows values below 0, the type whose name starts with the int prefix, or unsigned, that doesn't, though can store 2 times larger values above 0, whose name start with uint prefix. Like with floats, you can also set the amount of storage by adding the numeric suffix age, 16, 32, or 64. There's also the byte data type, which is an alias for int 8. And the last scalar data type is called run, and it is used to store string characters. This data type is an alias for the int32 data type and is used to store Unicode code points that are used to build strings representing textual information. So, as we are familiar with almost all basic data types, let's see what they can be used for. As we said, bool data types serve as a result of logical binary operations: less, more, equal, more or equal, less or not equal, and unary operation exclamation mark, meaning not. Let's print a result of a simple logical operation by defining two integer numbers and comparing them. As you can see, 5 is not bigger than 10, that's why the output is true. Also, note that you can only use variables of one data type to compare them. You cannot compare number and a string. Now about numeric types. All numeric types support typical mathematical operations that you have known from school: multiplication, division, addition, and subtraction. More complex operations, such as taking the square root, can be found in standard library or third-party packages. Let's see an example of a simple formula to see how you can make calculations. Also remember that you can use brackets to change the priority of operations. By default, they are the same as in pure mathematics. As for runes, you cannot do much with runes except comparison. It's more useful to discuss string operations, and we're moving to them just now. So, the last data type that Go developers consider as a basic one is a string type, which stores textual information. In Go, string is basically a sequence of bytes representing some text. Let's define a string and initialize it with some simple predefined value. The goal of strings is to store textual data. In Go, strings are just read-only sequences of bytes. So, in order to know what text is stored in a string, we have encodings. GoStrings does not expect your bytes to represent certain encoding, so all manipulations are up to us. In our case, we will use string literal. The source code is UTF-8 encoded, so string is also UTF-8 encoded. Actually, we have been working with strings so far in all applications that we've written before, and you already know that strings can be used and formatted for output with FMT package functions. There's also a useful strings package that provides a large set of functions for string processing. You can find information about it in an official documentation at golang.org. So, we have familiarized ourselves with all basic data types that Go language offers for storing data in the main memory of our machine. Now we are ready to move on and discuss pointers as another core concept of working with memory. By now, we know what data types we can use to store data, and it's time to get acquainted with one of the most significant concepts of working with memory: pointers. When we declare variables of certain data types, we use them to access the value. When we pass a variable to a function as a parameter, that value is copied in memory, and the function actually works with a copy that lives all the time the function runs and is then deleted from memory. The first, if we want the function to change the initial value stored in variable, and the second, if we don't want the value to be copied because it takes a large amount of memory and thus is a subject of optimization. If you are familiar with pointers in C language, it seems important to tell that pointers in Go do not support pointer arithmetic. Let's get back to our example code 1.4 from the first section of the course when we used scan function from the FMT package to receive user input. You can mention an ampersand sign there. Ampersand is a syntax element that gets the pointer value to be stored in a variable. So, we are near to the pointer. The pointer is an integer value that stores memory addresses, unlike a variable that stores the value. Returning to our scanf example, we need to pass a pointer to the function so that it can save the input value of an address represented by pointer. If we will pass the non-pointer variable, we will not be able to do this because we will work with a copy of an original variable. Let's see how we can declare pointers. Let's declare a simple int variable and initialize it with a value. Let's print both values by running this application in the command line interface. As you can see, we have printed a value and another number that actually represents an address of that value in the main memory. That is the nature of a pointer. Now, when we know how to get a pointer to a variable, it's time to perform a reverse operation. I mean accessing a value through the pointer. This can be done with an asterisk operator that is placed before a variable identifier. So let's update our code and change the variable's value through pointer and print out the results by running our application. As you can see, we were able to get access to value through the pointer, which you'll find very handy in the future. At this point, you may ask, what is the value of the pointer before its initialization? And I would say that the value is nil. It's a reserved keyword denoting that the pointer does not point to any address. Every data type has its zero value assigned to it by default, 0 for numeric data types, false for booleans, and empty string for strings. As we have finished dealing with pointers, let's make some conclusions. Pointers serve two purposes. The first is increasing the efficiency of memory usage, and the second is being able for different parts of your code to get the right access to a certain address in the memory, as demonstrated in the scanf example, for changing the data stored there. Also, Go pointers do not support pointer arithmetics. There's also an interesting fact that most of the complex data types in Go can only be used as pointers. You work with them as you do with simple variables, but you have to remember that they act like pointers. These data types include slices and maps, which we are going to talk about in the next part of this section. As was told before, there are complex data types that are pointers by their nature. In this video, we will be talking about slices and arrays as instruments for storing large amounts of single-type data. So basically, both slices and arrays are sequences of values of a single predefined type stored in one single row in the main memory. The only difference between them is that the array has a fixed size and the slice's size can change during runtime. Let's define a slice of integer values to see the syntactical aspect of those data types declaration. As you can see, for the moment, the syntax is pretty similar except the square brackets that identify that the variable is a slice and not a scalar value. You can also initialize slice with starting values by specifying them. Let's see what it looks like. And to finish this part, let's print out the slice to a command line interface by running an application. Slices are used to store sequences of values and their processing. So the first thing we have to learn is how to access single elements of them for reading and writing data. It is done with square brackets by specifying the element index inside. Note that the first element index is 0 and the last equals to size minus 1. Let's print the second element out of slice. It's not necessary to declare a new variable for this. We can put an expression itself as a parameter to the println function. Similarly, we can modify this value by assigning a new one. Let's assign a new value to the old one for the element and print it out to the command line interface. It is also important to remember that slices and arrays themselves are pointer types. In our example, we have initialized slice with start values, although we often need to initialize slices somewhere else in the code. This is what the make function is needed for. This function also works to allocate memory for other complex types. Let's see the example of making a slice. If you want to create a slice, you should use the built-in make function. This creates a slice that is associated with the underlying int array of length 15. Slices are always associated with some array, and although they can never be longer than the array, they can be smaller. The third parameter 15 represents the capacity of the underlying array that the slice points to. When the capacity argument is omitted, it defaults to the specified length. Slices are very important in Go, so the language presents some built-in functions to work with slices. The first two are len and cap. They are used to get parameters of slice. Len takes slice as a parameter and returns a number of elements in slice, and cap returns the size of the underlying array. Let's change the S1 slice capacity to 25 and print out the results of calling len and cap functions on it. After running the application, you can see that len returns 15 and cap returns 25. You can also add elements to slices with the append built-in function. The function takes two parameters, a slice and something to add to a slice as a second parameter, which can either be a single element or another slice. In this case, the syntax demands to add ellipses to the parameter. The function returns the resulting slice. Let's try both in our code and run the application to see the result. There's also one important thing about capacity here. If the result of the append fits the capacity of the original slice, it uses the previously allocated storage. If not, a completely new underlying array will be allocated. So be careful, as it will not only receive new pointers in memory, but will take more time for memory reallocation itself. As slices rely on some underlying array, arrays can be used to receive slices of them with the slicing syntax. You can specify the start index and end index split by using colons inside square brackets to get such slices, as shown on screen. Since Go 1.2, it is also possible to specify the third parameter, the capacity of the resulting slice. The slicing syntax can also be used on slices themselves. If you slice a slice and save the results in the same slice, the technique is called reslicing. It is quite efficient because it reuses previously allocated data slices and eliminates the usage of additional data copies. And the last useful built-in function that we have to mention is copy. It takes two slices and copies data from the slice denoted by the second argument to another one. Note that copy will copy as much elements as it can, so if you want to copy a larger sized slice into a smaller sized one, not all elements will be copied. That's all for slices. Let's move to arrays. Arrays are quite similar to slices, except that they have a predefined size that cannot be changed during runtime. So, in this aspect, they are less flexible than slices, but at the same moment, they are more efficient in work. And the other difference is that the memory for array is allocated at the moment of declaration, while slices have to be allocated with the make function. Another thing about array types is that array types are identical if they have identical element types and length. This is important because variables that point to different array types cannot be compared. That's all for slices and arrays. These data structures are useful for implementing storage and processing of value sequences of one type. One of the best ways to use these data types is using multidimensional arrays and slices that are used to represent matrices, and this is the subject of our next video. Let's continue working with the arrays we started while doing the previous task. The thing we're going to discuss in this video is multidimensional arrays. The same can be applied to slices, so we will discuss features of multiple dimensions only for arrays. The main point of multidimensional data types usage is implementing matrix data types and larger specific data structures. For example, hypercubes, which are widely used in building online analytical processing software. So let's start with the declaration of the two-dimensional array. The syntax is pretty similar to how one-dimensional arrays are declared, except that we add one more pair of square brackets. This way, you can interpret a newly created structure as an array of arrays. If you add more bracket pairs, you receive 3, 4, and so on dimensions for your data structure. One of the most widespread tasks done with matrices is matrix addition. It is possible for matrices with equal dimensions, and the result of the operation is a matrix whose element values are the sums of the corresponding element values of two matrices operands. So let's define another matrix in the same way as we did with the first one. And the last thing we need to do is to declare the resulting matrix whose elements are simple additions as shown on the screen. Let's print the results and run our application to see the output. If you're not using short declarations, you can declare the two-dimensional array variable with the var keyword and then continue working. It's not necessary to allocate memory manually with the make function. The same syntax applies for more than two-dimensional arrays, as you can see it on your screen. So when you perform access to elements of such arrays, you also use that number of square bracket pairs to specify indices of elements as you've used while declaring a variable. As you can see, adding matrices is quite simple when a matrix is small. However, consider you have matrices with thousands of elements. Such implementation of additions won't make you happy. We will get back to this task in the next section during the discussion of ways to implement run loops and how can they be used to solve repetitive tasks. However, in general, the current task gives you enough insight about how sequences can be efficiently stored and processed in memory, and we are ready to enter the last chapter of this section, called maps. During last videos, we have familiarized ourselves with arrays and slices and how they can be used for working with sequence of values. This video will lead us through the last widely used standard complex data type called map. Maps are used to store sets of key-value pairs. Consider that you have to translate some text, and you use a dictionary for that purpose. What you do is basically searching for a word in a source language, and then you see its translation. This is how mapping works. You have some key and some value bound to this key. You must also take into account that in one mapping all keys have to be unique. Mapping is also typed, so when you declare a mapping variable, you have to specify the type for keys and another type for values. The same way as slices, Mapping also has to be allocated with the make function, unless you initialize them with some starting values. Let's see both cases on screen. In the first case, we will initialize mapping, and in the second, we will allocate memory for it with the make function. You also have to notice that the initialization syntax uses colons between keys and values and not commas. Using make keyword, you have to specify the type of mapping and initial size of it. The size of mapping can shrink and grow during runtime. So now you know how to declare maps, and we are ready to learn how to add elements to mappings, change them, read them, and delete them. The access syntax is pretty similar to slices and arrays. The only difference is that instead of the index inside square brackets, you have to specify the key. Remember that the key has to exist inside mapping. Another case will be discussed in further sections. So let's print a value for a key this way and run the application to show the results. In pretty much the same way, you can add or modify values for keys by accessing them and assigning some value with the assignment operator. Let's try it in our source and print the wall map after. As you can see, this way we can either modify or add elements to the map. And the last operation we are going to do is deletion. You can use the built-in delete function. When you call it, you specify the map you want to delete the element from and the key. Let's delete the element with the key 1 from the dictionary and print the whole dictionary to the screen. As you can see, after the deletion, we have only 2 positions inside the map. Maps are used for different purposes in Go applications. The most popular ones are serialization and caching tasks. Serialization is a way to represent in-memory data the way it can be suitable for writing into some external data storage, such as HDD or network socket. Let's use another standard library package, encoding/JSON, to demonstrate how can maps be used to serialize data. JSON stands for JavaScript Object Notation and is a popular format for information storage and transfer. Let's create a map with string keys and string values and serialize it into JSON. Here we use the JSON package's Marshal function to receive a slice of bytes that can be used to export data from the application. We will just print the results out to see what they look like. The opposite action, loading data into the in-memory structure, is called unmarshalling. It will be great for you to make unmarshalling as a small task. Visit the documentation on JSON package at golang.org in order to get help. I congratulate you on finishing the second section of our video course. So far, you've learned how to work with variables and standard data types, and this is the point where we are ready to move on to controlling structures section and writing more complex and useful applications using conditional and looped execution of code and processing errors. In the previous section of the video course, we have learned how we can work with in-memory data using variables and constants. We have also written some simple applications, and now we are at a point where we are ready to start working with more advanced concepts, execution flow control. So we start here with conditional execution of code using the if statement. Let's look at the next problem. You're building an application that is not approved for all audiences, so at the beginning you have to ask the user about his age. If he is 18 or older, the application continues to work. If not, we tell him or her about the restrictions and finishing execution. So the main problem here is to make a check of user input and decide what source code must be executed. Here the if statement becomes useful. An if statement checks the condition, which is a result of some Boolean operation. In our case, it is the greater than or equal operation, and the if statement executes its body enclosed by curly braces. If the resulting value is true, the body is executed. If not, The execution passes by starting the next statement after the if block. So let's make our application print different text lines depending on the user's input and run the application to test it. Let's input the number 20 and press enter, and we will see the congratulations text on screen. Let's run an application again and enter 15, and we see the sorry, you're too young text. So the goal was achieved. Using the if statement, we are able to control whether or not a piece of code will be executed. That was the simplest case of making a decision. You possibly mentioned that in our case, if the user entered a number below 18, the application executes the last line of code and stops, and this line is executed in any case, as if there were no if blocks before. Go offers an extension to an if statement that tells the code that another block of code must be executed if the condition was not met. It is achieved by adding the else block. Let's put our printing into the else code block. As you can see here, we enclose it into curly braces the same way. That's it. The block will be executed if the condition was not met. Let's run the application and test it, and we will receive the same result. While this example of using else is interchangeable with the code before, let's make our task a bit more complex. Let's say that our application has advertisements targeted for different audiences. For young people aged between 18 and 30, we show one kind of advertisements, and for people older than 30, another advertisements. So obviously we have to add an additional block of conditional execution. On one hand, you can use the nested if statements, an if inside another if block. And it's okay. But on the other hand, it will make your code less readable, so we will use the combined else if to add another conditional block. Let's add it between the blocks we already wrote and change our first condition to check if the number is greater than or equal to 30. Let's run the application and type 20. As you can see, only the second block was executed and other was omitted. So when you have such kind of tasks where you have to make decision and or if some code blocks must be executed when meeting certain conditions, you have to build a construction using if. Let's look through the last feature of the if statement. The if statement allows us to declare a variable right before a condition, and this variable will have a scope restricted to the if code block it belongs to, and all its continuations, such as else if and else blocks. Actually, you can declare any variable in that slot, and it does not necessarily need to be used as a part of a condition expression. This is how it looks like. Let's declare a simple string variable. You must also remember that this variable must be used somewhere inside the code block, otherwise you will receive a compilation error. Let's run and see it. The if statement is the most general way to make your application decide what pieces of code must be executed in certain conditions and what must not be. The other way to organize conditional execution is the switch statement, which we are going to discuss in the next video. In the previous video, we have learned how conditional code execution can be designed using Go. The if statement itself is very general and can be used everywhere. In this video, I would like to introduce you to another way of doing conditional code execution, the switch statement. While the if statement is very general and works with general conditions represented by Boolean expressions, the switch statement is used as a partial case of if for enumerating cases. Let's consider the next task. You're developing a text-based role-playing game where the user moves his or her character throughout the world. And the typical situation is a crossroad where the character can move north, south, east, or west. You have to receive the user's input and decide where to go based on it. By now, you should be able to do this task with the if statement by writing if-else blocks. However, this can be done in a more readable way using switch. Let's write down the solution for our task using switch. First of all, we put a variable which is checked. Then we enumerate cases. For every case, an equality check is done implicitly. When the code executes, only the first matched case will be executed, and then the execution continues after the switch block. There is also a special case called default that is executed if no other cases were matched. As with the if statement, the variable can also be calculated right here and will be visible only inside the current switch block. It can be very useful for our task. Let's say that it is not important for us if the user enters a letter of the direction for his or her character in lowercase or uppercase. Thus, we can pre-calculate the switch variable to bring the input to lowercase. Let's make it and test it by running the application and inputting the uppercase N letter. As you see, the character goes north. By doing this simple operation, we have made our game's interface more friendly. And the last way to use the switch statement is not to specify the conditional variable. In this case, the statement behaves like if, and we don't use values in case statements, but specify Boolean expressions. Let's return to the code from our previous video and see how we can rewrite it using switch. Here, we just change if to empty switch and every if-else block into case blocks. The last else block turns out to confirm the default block of the switch statement. The switch statement proceeds sequentially condition by condition until some condition is met and then finishes executing. But in case of a situation when you would like to continue condition checking for other cases, you can use the fall-through statement. Let's add another case, x less than 18, in which we print kid on screen. It is also important that the default case remains, so we add fall-through to the last case to make this happen. In our examples, cases were quite short, but sometimes cases contain more code. Certain parts of it must not be executed. In this case, you can use the break statement to finish the switch statement execution prematurely. Here is how it works. If you run and test your application, you will see that it behaves the same way as in the previous variant. It's up to you to decide what kind of statement you would like to use more. Just remember that it is more common to use switch for enumerations of possible variable values, and the if statement for applying general conditions. Through the last two videos of the section, we've learned how to branch our code in certain conditions. The next and one of the most important topics in Go and programming as a whole is how to make cycles, repetitive executions of code blocks, and it is the subject of the next video. In the previous video, we have learned how conditional code execution works. At this point, we are going to discuss one of the most important concepts, cycles, or more commonly called as loops. Loop is a way to execute a piece of code several times sequentially. The best way to illustrate how can loops be useful is a classic task of finding a sum of array elements. Let's assume we have an array of integer numbers representing monthly salaries of employees at some company, and you would like to make an application that finds out how much money does the company spend on salaries per month. The problem is that in general cases, you don't know how many employees are there in a company. You just have a simple array of salaries. Let's start with a minimal application and define a sample array in the code initialized with several values. In real life, these values can be received from a database, file, network, or any other source. But for simplicity, we will hard-code it in our application. So the algorithm for solving tasks is pretty simple. First of all, we declare a variable in which we will store our results. It is initialized to 0 by default. Next, we have to add each element of the array to this variable in order to get desired results. So the addition is what we need to repeat as many times as the size of our array is. Go offers the for statement to organize loops. It has 3 slots in its header delimited by semicolons. The first, the iteration variable definition. An iteration variable is a variable that changes its value every time the loop body executes. That is why loops are useful. As variable changes your loop body, the code can be executed on different data. Let's declare it for our case. We will use it as an index in order to get access to array elements. The second, a stop condition. It is a Boolean expression that is executed every time before the loop body executes in order to check if the loop must continue or be stopped. In our case, the loop must work until the variable value will be less than the size of our array. The third, a statement for changing the value of the iteration variable. In our case, we must increase our variable value by 1 in each iteration. And the last thing is to add the body. Let's add code inside. And at the end, we output our sum to the screen and run the application to test if everything works. As you can see, the sum was calculated and we received the expected results. Another interesting feature of the for statement is that all variables you declare inside the statement's body are restricted in scope to that body, so you can't use such variables outside. It is very useful if you have more complex code and you use temporary variables for storing intermediate results of your calculations. Let's move ahead. In the previous example, we have used all slots of the for statement, but this is not necessary. Sometimes you don't have explicit iteration variable, but you want to execute your cycle until some condition is met. Let's consider the next task. We ask the user to input an integer number whose value is greater than 10, but the user may not listen to us and enter any value he wants. Here, we can use only condition slot to ask users for input until the condition is met. Let's rewrite our loop for new task, run our application, and try to enter values lesser than 10. Now, add one value greater than 10. As you can see, the loop body is executed until the condition is met. Other programming languages introduce separate operators for such kind of loops with condition, usually called while, but Go developers decided to unify all kinds of loops in one for statement. Another interesting loop type is an infinite loop, which can be implemented through the empty for statement. This kind of loop will be executed forever. It's very convenient, for example, for implementing event-driven applications such as web services and graphical user interfaces, where all applications are an infinite loop. Though the loop can work forever, Go language offers you ways to control its execution manually using break and continue statements. The first finishes cycle execution right at the place, and the second finishes current iteration execution and passes right to the next one, recalculating everything that was specified in a loop header. Let's write an application that calculates the sum of all odd numbers using infinite loop and cycle execution control statements. First, we declare the iteration variable, not in the cycle header, but before, just to demonstrate the concept. We increase its value by 1. Then we check if it is already 10. If so, we break execution. Next, we check if the number is odd, we add it to our sum variable. If not, we continue to the next iteration. Run application and check if everything works as expected. Loops is the most widespread concept used by software developers. Among other ways of usage that were discussed, loops are used for different tasks. Remember the example with matrix addition from the previous section of the video course? It can be easily done with loops for any size of matrices. Loops can be nested, so you are free to use the for statement inside another for block. This will help you iterate over matrix rows and columns. Loops is a heart for most algorithms, and now you are ready to use them in your application. Now, let's move on to the next video, throughout which we will discuss error processing. Now, we are going to get familiarized with error processing in Go. Go has two situations when your program does not execute as it was planned: execution errors and runtime errors. In this video, we are going to discuss the first type of errors. These kind of errors happen when some code cannot be executed as expected. Consider the next situation. You use the scanf function in order to ask the user to input the integer number from the keyboard. However, he actually can input everything he wants, basically any text string. The Go application won't know how to convert a string containing letters to an integer, so it will inform you about an error. So, an error in Go is an object of the type error. It represents a text string inside, which is made for developers to indicate that something was wrong with the code. Developers can use these objects to check if an error has happened and to process it somehow. Let's look at this more practically using the scanf function. Up to this point, we have been using the scanf function without looking at the value it returns. Going forward, I would like to mention that Go functions can return any number of values they would like, and when you call a function, you must enumerate all these values as variables to store them, separated by comma. We will discuss it in depth when we will be talking about functions. Scanf is a function of such a type. It returns two values. The first is an integer number of scanned values from an input, and the second is an error that happened during function execution. If there was no error, the value defaults to nil as a default value for a pointer. Let's consider the next task. We ask the user to enter an integer number, but we must process his input in order to check if he did input an integer number or something else. Let's use a loop for it. We will execute a loop body consisting of the scanf call and error-checking if statement. If there was no error, we just break the execution. Let's run an application and test how it works by entering integer and non-integer values. As you can see, it works as planned. Now you know how to process errors. Actually, a lot of functions return errors if they can happen inside, so you have to check the documentation on functions you use to see if an error can happen. You can also create custom errors for your applications, but this touches some topics we didn't discuss yet, so we will return to the topic as the time comes. Error processing is a must for almost all applications. Errors often happen for different reasons, and one of the most popular ones is a bad user input that does not conform to your algorithms, and now you know how to deal with it. It is worth mentioning why error is returned at the second parameter for most functions in Go. The rationale is that most errors in a program should be checked and reconciled. Instead of making it a special construct, the error is just a returned value. In the previous video, we have discussed error processing in Go. The current video is devoted to the "OK" notation, which is another way to deal with the unexpected behavior of your application. The "OK" notation is also connected with multiple return results of a function or operation, but it usually means that before executing a function or operation, some additional implicit check was done, and it cannot be executed for some reason. Let's look through the next task. You have a map, and you would like to get a value with the key. When we discussed maps, we restricted us to a case when there's a key existing in our map. But the problem happens when there is no such key you would like to get a value for. In this case, when the key is not present in a map, you will have zero value, which is the default for the map value type returned. For example, if the value type is string, an empty string will be returned. However, the value across operation represented by square braces can return two values, and the second value is a Boolean value that indicates whether the operation can be finished successfully. In our case, if the specified key does not exist, the second value will be set to false, and it will be set to true otherwise. It is common to name the second variable OK, and that's where the name "OK" comes from. Let's use this notation to check if the key is present in a map. As you can see, it looks very natural in a code with an if OK statement. You can also use this to test if the key exists without getting the value itself. It is done by changing the v variable to underscore. Remember that the Go compiler requires a variable to be used if it was declared, And underscore is a special variable that indicates that the returned value is not important for you and you won't be used further. As you can see, OK is somewhat similar to what an error is, as was described in the previous video. There's a thin edge between when you can use errors or OK. Errors are usually used when a real error occurred. For example, a packet with data cannot be read from a network. And the OK approach is used when you have to use some additional checks before a function or operation executes its remaining body. At this point, we have finished our last video from this section, and we are ready to go ahead to the next one, where we are going to learn how to design the application structure for larger applications using functions and packages. Welcome to the first video of section 4. In this section, you will learn how to design large applications in Go and how to split your code into logical sections in order to make your code maintainable. The first technique was writing comments for your code, but consider a situation when your application grows larger and has hundreds and thousands of lines of code. At this point, we know how to write the application code inside the main function. But having tons of code in one file and in one function will make it impossible to read and develop within a software developer's team. Let's go on and learn the first way of splitting your code into pieces: functions. We have been working with functions so far either by calling built-in functions such as delete to delete keys from mapping, or functions imported from other packages such as println from the fmt package. Also, we wrote the main function. Yes, main is a function too, though you never call it. When an application starts, this function is called by default as a starting point for your application, and when it finishes executing, your application is finished too. Let's consider the next task. You're writing a mathematical software that solves equations, and the user needs to solve the square equation. Actually, you are ready to solve this task by now, so let's look at the screen where the solution is already implemented. It's quite a good implementation if you want to solve the square equation only once, but in real life the user does different actions with your software, and he will want to solve the equation time and again for different cases. With the current approach, we must copy and paste this code everywhere in an application where the solution must be provided, and this is not very handy. Let's move it out to a separate function, solve square equation. The function is declared starting with the func keyword, then the name of the function, then brackets, and then curly brackets open where we put the function body. So let's move the code into a new function and call it from the main one. As you can see, it works as expected, and our main function contains only one call. Now we understand the whole flow of the application more transparently. Let's move on. The solution is quite good, but in our case we rely only on the keyboard input, so the solution is not quite general. If we would like to take an input from a file, we have to write one more function. And the purpose of the function is to be as reusable as possible. We cannot repeat the same code time and again. It actually causes bugs, because if you have to rewrite something in the future, you will have to do it in several places. So let's move our input code back to main, but you must say that it won't compile. Yes, it won't compile because our solve square equation knows nothing about a, b, and c. That is what parameters are for. Parameters are predefined values that we add to a function to show what variables we give it to work with them. In our case, these are a, b, and c. Adding them will allow us to solve any square equation, and the function is not concerned with where these values came from. Parameters are declared inside brackets after the function name. Let's write them down, call a function with parameters, and run the application. Yes, it works as expected, and now the function is reusable enough to be used everywhere in our application. However, we have another problem. What if the user doesn't want to see the results on the screen but use them somewhere else for other calculations? Considering that our function is not usable, and here what are return values for. A function can return either single or multiple values, and the syntax is the same for both. We need to specify return values after the brackets with parameters, except that if you have only several return values, you have to embrace them with brackets. If not, you can just write the return type identifier before opening the function's body. In our case, we have to return 3 values for appropriate processing: number of routes, first route and the second route. Let's write these types down in brackets after parameters definition and print the result of the function inside the main function. Let's run the application. As you can see, everything works as before, but our function serves as a fully independent piece of code, which does minimally what it must do, and it won't require rewriting no matter what you use it for. You can write functions to return errors or results in the style of the "OK" notation in the same way as we return multiple results. In our case, an error can happen when a equals to 0, so we would possibly like to add an additional check on this, and also add a fourth parameter on default to 0 routes, as with the d less than 0 case. And the last small topic about functions in Go is that functions can receive variable parameters. Remember the println function? You can pass different number of parameters to the function, and it will print them to the screen. This can be achieved by adding ellipses to the parameter's name in the function's parameter list as shown on the screen. In this case, you refer to the parameter as a slice, but when you call such functions, parameters are passed separated by a comma as if there were several parameters declared. Let's try to call our println function with 3 parameters and run the application to show the result. As we can see, functions can be very useful to decrease the size of your codebase and improve your software in order to avoid bugs in your code. Along with writing larger software, you will write most of your code in functions and leave your main function just for organizing the flow of your application on the highest level. Now we can move on to the next video to continue learning some other possibilities of functions in Go. In the previous video, we have discussed the syntax and purpose of functions as reusable blocks of code, and in the current video we are going to look at functions from the other side, and here I mean considering functions as values. Yes, functions can serve not only as reusable parameterized blocks of code that return values, but also can be considered values themselves. Also, they can be written inside other functions. Let's consider the latter. You can write functions inside other functions in Go. These functions can get access to non-local variables. Basically, to variables of embracing functions. Such functions have their own name, closures. Let's change our solve square equation function from the previous video by moving discriminant calculation into a separate function. As you can see, our function does not have its name, but it is bound to a variable that can be passed around. The only difference between an ordinary function and an anonymous function is that the latter has no name, but anyway it must be assigned to some variable. It doesn't make any sense for the current task, but demonstrates the concept. The only thing you receive with this approach is that you cannot call this function from outside the solve square equation function. Really, you don't need to calculate discriminant for anything else other than the solve square equation. So making closure is good in this sense, and if you find such a situation, it is worth the effort to write a closure if it is reusable, though in our case it is not. You can run application and see that nothing changed. The application still solves the task. Also pay attention to parameter names. We defined A, B and C for closure, and they have overridden solve square equation names, so these are different entities. If you have named them with another names, you could use A, B, and C from the outer function, and it is another feature of closures. Now we can move on to see how functions can be treated as values. Let's consider the previous video example. In the last task of the previous video, we have moved out the display code from the solve square equation function in order to make the function as much reusable as possible. But there's another way to parameterize the output of the function. Pass a function that makes the output as a parameter to the function. Actually, the parameter set and return value set together make up a function type. So if we want to make our function accept another function as a parameter, we add another parameter followed by the func declaration but without a name. A parameter name will be treated as function name. Let's rewrite the whole application so solving the function will output with the help of our new parameters. As you can see, you can operate with this parameter as with an ordinary function, though through another name. We will also write our new function to print results that confirms the specified entity at the fourth parameter. And we also change the main function to call solve square equation by adding a new parameter in a function call. Let's run an application and see whether it operates as expected. Closures are anonymous. It means that they are assigned to some variable at a place they are defined as closures, as we saw it before. Let's remake our myPrint function and use it inside the main function's body at place. To do this, we remove the myPrint function and add the anonymous function right at the place where we call solve square equation. Let's run the application. As you can see, everything operates like expected. The most typical usage of anonymous functions are adding reusable pieces of code that are specific to some functions and cannot be used anywhere apart from their location. Callbacks, as was demonstrated with the printing result of solve square equation tasks. Basically, callback is a function that is passed to another function as a parameter. It is used to pass not only objects to functions, but also whole algorithms. Callbacks are often used within an event-driven development paradigm. Using anonymous functions often adds flexibility to your code with organizing your code on callbacks and also allows you to encapsulate related application logic in one place. Also, you can decrease your code size by implementing and calling small functions in place as was shown in our last task. At this point, we have finished discussing functions and we are ready to learn the largest part of your application, a package. A package basically is a set of package variables, functions, and other code pieces we haven't discussed yet, such as structures and interfaces. A good package is a package where all these entities serve to solving some set of logically connected tasks. For example, the package math from the standard library contains mathematical functions and constants, and in the same way it has nothing to deal with databases. So here is the first rule of thumb. If you have some functions and constants that implement some business logic in the same area, it's a good idea to join them into a package. We have been working with packages so far. You actually know how to import packages and how to use functions and the constants declared inside them. And you have also been writing a package code all the time. Yes, the main package. Along with the main function, it is the root package of your application where everything starts to execute. To create your own package, you have to create a folder inside the src folder of the workspace you're working in. This was discussed in section 1. All Go source files inside that folder may be referred to that package if they start with the appropriate package declaration string. Let's create our own package equations and use the code from the first video of this section where we wrote a function that solves square equation. We were considering writing mathematical software there. So we might want to add in other solvers in future, and it is a good idea to join such solvers into one package. Let's move that function into a package and call that package equations. Packages can reside in your Golang distribution, remember GoRoot, and inside your workspace, GoPath, and the src folder is a root for your imports. So in our case, it will be the equations folder inside the src folder. Here we create sqr-go and move this function inside that module. Note that it is impossible to add subfolders for your package, but in that case you receive a subpackage, which name will consist of your current package's name, then slash, and then the subpackage name. We already used package encoding/JSON from the standard library, and now you know the way it is created. Another thing about package that you must know is that packages are able to enclose details of their implementation. It is done with unexported functions and variables. The rule is very simple. If you want something from your package being used from another package, start its name with a capital letter. All other entities will be treated as unexported and can only be available from inside that package. You can test it by importing the equations package from your main package and trying to run the code that solves the square equation. You will get an error, and you have to do everything to fix it. That is, start the function name with a capital letter. Let's make that small change in the function declaration and in the place we call it. Let's run the application again. Here it is, works as expected. So far, we have written our first package and used it to link to our main application. As you can see, we now have only equations and FMT packages imported in our main package. The math package is imported inside the equations package. As our application is solving equations, we basically don't need anything else, and our main package looks like very nice now. Let me say a few words about the unexported functionality. It may seem not very useful for now, really, why would you write something that you can't use in future, but unexported package variables and functions can be useful if they perform something you would not like other people to use in order to make the execution of your software safe. For example, you can use unexported package variables to store session cache if you are writing drivers for a database. If users get access to it, they can break your caching system. And another popular reason is to hide functions that are used for testing, debugging, or doing some intermediate job and must not be called directly. In our case, it can be a function that finds discriminants. You can move this calculation to a separate function and make it unexported. All such things are treated as a private API, which is not accessible from other packages, and exported things make up your public API. This also can be treated as encapsulation, though this term is more often used while discussing object-oriented development. That's all for the current video. We have discussed how to write our own packages and thus separate our application logic into independent reusable parts. And we have one more video to discuss package initialization. In the last video, we were talking about packages and how they help to make your code more maintainable by breaking them into independent pieces containing logically connected functions that operate in one domain. Go language developers paid a lot of attention to initialization process by providing developers a tool for resources and variables initialization. Not every variable in your code is initialized with a zero value or just some predefined constant. It often happens that you have to initialize variables with more complex values. For example, you would like to have a mapping with integer keys from 0 to 100 for some purposes. The problem is that you cannot write any code except declarations outside functions, and on the other hand, writing everything in the main function or other function that you are going to call yourself can cause errors just because you forgot something. Here we have to mention that the first thing that is executed in a code module, not package, is variable declarations, and then the main function, and all that is called after. But Go offers special init functions that cut in this process and start to execute right after the declarations were processed. Moreover, you can have more than one init function in one Go source file. Let's practice some. Consider the next task. We have a map of integers to strings, and we would like to initialize this mapping to have keys from 0 to 9 mapped to empty strings at the start of the application. First of all, we declare the map of the needed type. Then we write the init function with an initialization code. And to check if everything works as expected, we print the map inside the main function. Let's run application. As you can see, the mapping is not empty, though the main function has only a printing call. So the init function worked for us. There's also another common practice in Go to use init functions, a register pattern. The main purpose of this pattern is to get access to an object dynamically by requesting it from another object called registry by its name, rather than hard-coding object usage. Don't be afraid of the object term. We are going to discuss object in the next section, so get ready. A good example of this approach is the Golang database/SQL package. It has an exported registry and the exported function register that allows you to register your driver for a relational database. And the register function is called inside the init function. So, if you would like to change your database during your project's lifecycle, you would not need to care about rewriting your code. You would only have to find an appropriate driver and import its main package. After that, everything will work fine. Only if that package is written in a specific way, of course, but we will talk more about this in the next section. There we'll be discussing interfaces and advantages of object-oriented development. At this point, we finish our discussions on packages and their specifics, and we are going to discuss the last topic of current section, deferred code execution. So let's move to the next video. At this point, we have learned the basics you have to know to design applications of any size organizing the source code in packages and functions. And we have one small topic about functions to discover: deferred execution. Deferred execution is a mechanism that was introduced by Go developers in order to introduce bug-free resource management. Till now, we were only working with in-memory data, and the data was received from a keyboard, but in real world, you will have also to deal with other sources of data, such as network connections, including getting data from databases and web services, or peripheral devices, such as a hard disk drive. Such sources of data are usually called resources. A typical example of a resource is an open file on your disk or an open connection with server. The workflow is usually as follows. First of all, you acquire a resource. For example, you open a file on your disk, and as a result you receive the file descriptor. Then you work with your resource. Modern operating systems do not allow you to work with resources directly, so this descriptor is basically an integer number of an open file that you will ask your operating system to work with via supported functions, such as reading or writing. And the last step is freeing your resource. In case of a file, it is called closing. It often happens that the developer forgets to close the opened file or connection or another resource and receives errors or memory leaks as a result. A classical approach offers us to perform those three steps consequently, but it would be great if we could open a resource and just say, close it as it is not needed anymore. That is where deferred execution appears to be very helpful. First of all, let's look at the example of reading text from a text file. To save some time for us, I have implemented it, and you can observe how it looks like on the screen. Here in the code, you can see all those steps we have discussed before and performed on a text file. We open a file, we read the data, and we close it. The idea behind the deferred execution is to tell the compiler to execute a specified function after the exit of the current function. This means that the typical workflow for working with resources changes. First, we open the file, then we tell that we would like to close it as the current function has finished execution, and then we work with the resource. The syntax for the deferred execution is similar to an ordinary function call, but we add a keyword defer right before the actual call. Let's move the file closing call right after opening it and add defer. Now you can run the application to see whether everything works fine. We are also working with a text file here, and you can mention the path we've specified for the file. As we are running our app from our workspace directory, it becomes a working directory for our process, and that is why all paths to files are specified relative to this path. Though you can also specify an absolute file starting from the root path of your drive, this is not good as it would be specific for your machine and your app will be broken if you decide to move your application to another folder. That's all what deferred were created for, but you can also include your imagination and think of another use cases. For example, deferred execution can be used for implementing simple execution queue, and that is possible because you can call as much deferreds inside your function as you might want to. The only thing you must remember here is that all deferreds you add to your code are executed in the inverse order, so if you called 3 deferreds, the third will be executed first, and the first will be the last one to execute. You must also remember closures. Another way to use closures we didn't mention before is deferred execution. It makes the code much more readable if you write a specific function you need to defer at place rather than moving it out to a separate ordinary function. That's all about deferreds and structuring your code. So far, we have got familiarized with almost all control structures, simple data types, and code structuring techniques you will ever use for your Golang applications. And in the next section, we are going to discuss an object-oriented approach to building software in Go language. We will be talking about how to create your custom data types using structures, methods, and interfaces, and how they help in building reusable pieces of software. Let me introduce you the fifth section of the video course. In the first video, we are going to learn the object-oriented approach to software design and how it is implemented in Go. Object-oriented programming relies on an entity called the object, which has associated data, called fields, and exposes associated behavior. In this video, we are going to talk about data and how objects are implemented in Go. Objects in Go are represented by structures. A structure is a way to create custom data types consisting of several variables called fields, but accessed through one general variable. Let's look at a simple example. You have a passport or ID card that identifies you. It holds personal information about you, your photo, name, surname, and the date of birth. You could store these in 4 different variables, which is not very convenient if you want to store information about hundreds of passports, for example. So let's see how a passport can be expressed through a structure. First, we define the passport struct type. Open curly braces and enumerate all fields, each from a new line. Now we have a brand new type. The usage is the same as if it was a standard type when you use a var keyword for declaration, but this is a bit different when you use the short assignment operator. Here we add curly braces after the type name, and in case of the struct type, it means that we initialize all fields of that structure with 0 values. It is also called a struct literal. Another way is to initialize the structure with some explicit values. Let's see how it looks like. Note that the syntax is similar to how we were dealing with maps. We also place a comma after each field value. Let's run the code to see the result. Note what is printed and also 0 values initialization here. Now we are familiar with the definition syntax and ready to access data. It is performed via the dot operator. Note that all struct field names start from capital letter. The same rule as for exported package variables applies here too. You won't receive access to fields whose names start from a small letter in the code located in another package. Such fields are called private. In our case, all fields are public. Publics and privates is a powerful tool of encapsulation. You can define some helper fields in your structure that you would not give your code users access to. Same use cases as were explained in the previous section on packages exported variables apply here. Let's move on. In the second section of the course, we were discussing pointers, special variables that does not hold values but just addresses of those values in memory. You can also take pointers to structures the way you did before using the ampersand character. Also, while the variable stores only a pointer to the structure, it still allows to access actual values of its variables for reading and modification at its original address with the same dot syntax. Another way to receive a pointer is a new function. It receives type as an argument, allocates memory for your struct type, zeros fields values, and returns a pointer to it. This way, you can avoid ampersands, receive a pointer in place, and have a one line of source code economy. Some programming languages, such as C++, change the field access operator for pointers to denote that we are working with pointer, not a value. In case of the Go language, the syntax is the same, so you have to be careful having in mind if you work with the pointer or the value. This is very important because if you pass a struct value to function and try to modify it, the modification will happen with a temporary copy passed to that function. In the case of passing a pointer, you will modify the original value because you access fields by addresses. That's all on pointers. As you could see in our first example with passport, structs via encapsulation offers you a powerful tool for modeling objects. The object you model in a program is often referred to as abstraction. This is so because you always need only some subset of object features to work with. There is also another important principle of object-oriented programming implemented in Go called inheritance. The main idea behind this principle is to extend existing objects without rewriting the existing code. In Go, there is a special kind of field called anonymous field that is denoted just by the struct type name without the field name. If there is such a field in your struct, it inherits all fields and methods of the latter. Let's code a simple example. We define a vehicle struct that stores the number of wheels and another struct truck that has a weight it can carry. But truck is also a vehicle, so the vehicle's behavior can also be applied to trucks. So we add an anonymous vehicle field to truck. This automatically gives us a possibility to have the number of wheels already added to the truck struct. Let's check it by creating a new instance of truck and checking the field. When you run the application, you will see that it works. Now some notes on modeling. In our previous case, if we were working with passports, for example, accounting software, we won't care if it is printed on a paper or a piece of plastic. On the other hand, if we are making a software for ecology-saving organization, the physical material is actually what we care about, but not the person. We want more trees to be saved here. So talking about one real physical passport, we are talking about two different abstract models of passport intended to solve the problem of a software engineer in a certain domain. That is the principle of abstraction. During this video, we've learned how to work with objects and their data, and now we are moving to the next video to see another feature of the object's encapsulation principle, the behavior. In the last video, we were talking about structures as a part of object-oriented approach implementation in the Go language. We used them in order to encapsulate data. Now we are going to talk about the behavior. While data represented by fields is embodied in variables associated with a structured type, behavior is embodied in functions associated with a structured type. These functions are declared outside the structure body and follow all rules of declaration as ordinary functions. The only difference is that if we want a function to be a method, we have to define a structure type variable the method belongs to in brackets right after the func keyword. That structure variable is called a method receiver, and that is the way we associate a function with its structure to make it a method. This variable is available for use from the method and is the only way to access structure internals, such as fields or other methods. Let's look at our passport example and add a simple method that returns a full name of an owner. Here we will use the sprintf function that works similarly to printf but returns a string instead of printing results on the screen. Method is accessed via the dot operator exactly the same way as field, and to the end of the line the syntax is the same as if we've been calling an ordinary function, the method name and parameters in brackets. Let's add printing the result of the method call to the main function body. Here it is, we have successfully written and used our first full stack object. Let's move on. In our getFullName method's declaration, we use ppassport in brackets to denote a receiver. And this is an example of the value receiver. It means that when we call this method, the struct is copied in memory and passed to a method, which is a function by its nature, implicitly. It worked that way, but it is hidden by syntax. This is why such a way does not apply if we want our method to modify struct fields. You can yourself experiment to check this. As you could have guessed, the only thing we would like to change is to change the value receiver to pointer receiver so that we could pass an address to a method and work with the original data in memory. It is as easy as adding an asterisk before the type name. Let's write down another method that changes the name and surname of our passport carrier in one call, using the pointer receiver this time. Now we can change the main function body to call this method and then the other one that gets the full name to print it to the screen. As you see, it works for us. The rule of publicity is the same as with packages and structure fields. If the function name starts with a capital letter, it is considered as public, otherwise as private, and it cannot be called outside the package the structure was declared in. And the purpose of private methods is to hide helper functions from the package user. Public behavior of your objects in terms of general OOP theory, or a set of public methods of your structure in terms of Go language, makes up the interface for your object, something that other developer should use, and the interface is actually what the other developer cares about. In most cases, he or she does not want to know the implementation details, but the interface that says what can be done with that object, but not how it is implemented inside. Actually, Go cares about developers, and that is why it supports such kinds of types as the interface types, which is the subject of the next video. So now you can gather all knowledge you have got in this and the previous video on structures, fields and methods, and move to the next video, which discusses interfaces and the last principle of object-oriented programming, polymorphism. We have finished the previous video talking about polymorphism. It is a last core feature in the general OOP theory, which states that objects of the same type can behave differently, and interfaces is the way to achieve such behavior. Interface is a way to define external behavior of an object, and in Go it is defined as a set of methods that a caller can call with this object as a receiver. The syntax is very simple. It is defined similar to struct. First of all, we use the type keyword, then interface name, and then the interface keyword, and at last we open curly brackets to define a set of methods of the interface. Methods are declared like ordinary functions but without the func keyword. A data type is called to be the implementing interface if it implements all methods enumerated in that interface. Interface types are treated a bit differently in Go than in data types, but in most cases they are pretty similar. You can declare a variable of the interface type, but it will always be initialized with nil. This is important because the interface variable itself cannot hold any data, like data types, and at the same time data types can implement several interfaces. Let's look at the following example on the screen. We have two interfaces, I1 and I2, and an implementer struct that has both methods from these interfaces. We have declared an A1 variable of the I1 type. Then we assign new implementer to this variable, and the last we do is call both methods. This looks wise because implementer has both. Let's run the application. As you can see, the compiler shows the error A1 does not have method 2. So why is this? Well, that's because 2 lines before we told the compiler that A1 is of the I1 type. But fortunately, we can tell the compiler that the variables implement another interface. This hack is called a type assertion. The syntax is the next. We place the dot operator after the variable name and then type the name in brackets. This expression checks whether the variable implements that type, and if everything is okay, we can just use it. Let's see it in action in an example of calling method 2. If you run the application, you will see that everything works just fine. An interface assertion expression can also return 2 values in a manner of the OK notation. So the next returned value is a boolean that identifies that the type conversion proceeded without errors. And now about polymorphism. Let's look at the screen for the example of the strategy object-oriented design pattern implementation. The context is the next. We have a document and we would like to implement spell checker, but there are different algorithms to be used in different situations. For example, the simple spell checker works faster and can be used on low processor mobile devices. So we define spell checker interface that has only one method that checks the spelling of some text. And we have two implementations, ascstupid and ascclever. In our document structure that defines text documents, we have a method that sets spell checker and another method that uses it. And now look at the usage and the design. Document and checkers are fully independent of each other, and if we want another checker, we just create it and use it. The main bonus is that the almost zero source code should be modified for that. Also worth mentioning is that the spell checker type is used in our document, but the check methods are different, so a spell checker behaves each time differently, though it is still spell checker type. This kind of behavior is what we call polymorphism. That's all for interfaces. Interfaces are very good in gluing application components together. Actually, they can make it possible for our applications to be written in self-contained components, and it is a good practice to design interfaces first and then the implementation. As we are done here, let's move to the last video of this section, the universal interface. We have finished our previous video talking about interfaces and their purpose. The only thing we didn't talk about are special kind of interfaces, universal or empty interfaces. The empty interface has its name because it has a zero set of methods. This means that any data type will implement this interface. If you remember from the previous video, a data type implements an interface if it implements all methods of that interface, while an empty interface does not have methods, everything implements that interface. So, what is the purpose of that interface? Remember the println function we used in almost every example. Didn't you ask yourself a question, having all that knowledge about functions, how one single function can accept variables of all possible data types? The answer is here. Arguments are defined as universal interfaces. So this interface is basically used for incoming data that you don't have an idea of what type can it be. Let's look at the simple example and the syntax. The empty interface type is defined via the interface keyword followed by empty curly braces. Let's declare a variable of that interface, assign it some integer value, and print it out. As you can see, the variable easily accepted that kind of assignment. The most common task that an empty interface is used for is data deserialization. Serialization is a task of converting outgoing data stream from native Go language data structures to a stream of bytes. The opposite operation is called deserialization. So, if you write the serialization function, for example, you would like to convert your data into JSON format, you are forced to accept all data types in order to make your function be universal, and that is where an empty interface helps. There is also a reflect package shipped with the Go standard library that implements reflection, a feature of the programming language that makes available runtime inspection of data types. That's all on object-oriented programming. So far, we have come to an end of the current section in which we have learned how object-oriented programming looks like in the Go language. We also discussed principles of OOP and the ways they are employed to build applications. Let me introduce you to the 6th section of the Building Your First Application with Go video course. The section will be devoted to one of the core features of the language called goroutines. So, goroutine is one of the most important constructs of the Go language. When your application starts executing, one main goroutine is created, and in all examples we were doing before, we wrote a code that was executed in an implicitly created main goroutine. Go's runtime is supported by an entity called scheduler. Scheduler is a core part of the runtime that plans which goroutine should be executed on your processor or each processor if you have more than one. The scheduler uses the native OS kernel threads to multiplex running goroutines on them. The process of changing a goroutine to another on a specific thread is called a switch. Actually, you can have thousands of goroutines executing inside your application at the same time. If you have a multi-core processor or a multiprocessor machine, they gain an ability of parallel execution. But at the same time, you will have 2, 4, or at least 8 cores in your processor, along with thousands of goroutines inside your applications, so only 2, 4, or 8 can be executed in parallel, and the others have to wait for their time. The scheduler decides when to switch goroutines and gives each goroutine some time for execution. The algorithm is pretty simple. The scheduler will switch goroutines if they don't perform any CPU-bound calculations. So any input-output operation, such as reading, writing to file or network, or communicating on a channel, we will discuss channels in the next video, will make the scheduler to suspend the currently executing goroutine and invoke another one in a queue to have the CPU time for executing. A goroutine in the terms of code is a function invoked with the go keyword. Let's run several goroutines and see how they execute. Look on the screen. Here we define the function routine, which we are going to execute in non-main goroutines, and we create a cycle to create 10 goroutines in which the function will execute with different parameters. Let's run an application and see the output. Don't be surprised if you see our application printing nothing to screen. That is how goroutines live. Goroutine's life cycle starts when a function is invoked with the go keyword. At this point, it is added to scheduler, which plans it for execution when the next switch happens. Note that the main function continues to execute immediately, and goroutines wait for the scheduler to switch them. The goroutine executes only when scheduled, and this is not seen in our case because the main function finishes before that. So goroutine has 2 ways to die. The first, when goroutine's function finishes execution or the application finishes. When main function finished, it does not wait for goroutines to finish, they are just killed. Let's play a trick and put the main goroutine to sleep for 1 second. The sleep function resides in the time package, and it is a different case when switch happens, that is, when sleep is called. If you run an application several times, you can find that the order of lines each goroutine prints is different, and that is okay. Scheduler does not guarantee the order of execution, and you cannot rely on it when designing applications. Actually, you have a little control over scheduler through runtime package. The most used function is goSched, which forces the current goroutine to switch. It is very convenient if your function does not do any input-output operations, but you would like it to release some time for other goroutines. Let's add the goSched call before the sleep function and see that output lines have messed up even more. While time.sleep is the most basic way to wait for a group of goroutines to finish, there is a waitGroup object that resides in a sync package from standard library. Look through the documentation to learn the API of the object and try to replace time.sleep with a waitGroup. Consider it as a small home task before we can move on. As goroutines can be executed in parallel, they can get access to the application data simultaneously. Such data is called shared, and you must protect it from corruption when race conditions, situations where application behavior depends on order of goroutine's execution, occur. For example, you have a map that holds surnames and salaries for employees of some company. While one goroutine calculates the overall salary and the average salary to see the company's monthly expenses, the other can be used to add another employer to a company. It can happen that after you have calculated the first number, a new employee came and then you calculate the second number. Let's look at the screen where the current situation is implemented. We have used the goSched function in order to make data corruption more likely. Let's run the application several times until we get corrupted results. Here it is. The sum is 300 and the average is 100. The average was calculated after the employer was added, and the sum was calculated before. Go supports a classical approach to solving synchronization tasks that are widely used in multi-threading, synchronization primitives. They are declared in the sync package. Let's use mutex to see how can we avoid such situations. Mutex acts like a lock. When we use the lock method in one place, it would stop execution if we try to use it in another in parallel until the unlock will be called. So in our case, either the right value will be calculated for 2 employees or for 3, thus the data won't corrupt. The sync package also supports another synchronization primitives, such as rwmutex, which efficiently allows parallel access to data when the data is not modified, and conditional variables represented by the cond type. Conditional variables are used to block goroutine execution until some condition is met, which follows from its name. Though this approach does a good job in thread synchronization, Go offers a modern and easier-to-use approach to share data between simultaneously executing code called channels, and it is the subject of the next video. In the previous video, we have discussed the classical synchronization approach and mutex in particular, and the current section is devoted to channels. Rob Pike, one of Go's authors, once mentioned one of the core principles of development in Go: do not communicate by sharing memory, share memory by communication. While the first part of the previous sentence was discussed in previous video, the second part is what the channels were created for. In classical, they use data which is available for access from all execution threads and use synchronization primitives in order to check if a certain thread can read or write data in a certain moment of time. Go offers channels in order to change the pattern how these execution threads or goroutines cooperate and get access to data. While there are cases when the first way has to be used, such as caching, in most cases, channels is a preferable way to pass data between goroutines. So, what is a channel? A channel is an object that allows data to be passed in and received from, guaranteeing access synchronization. It means that if one goroutine sends data into a channel and several reads, only one reading channel will receive a piece of data. In this video, we are talking about unbuffered channels. It means that only one item can reside in channel at a time. So the write operation blocks until someone receives it, and the read operation blocks until someone sends data into the channel. The term blocking means that goroutine that performs such blocking operations will be switched until it is possible to perform the operation. Thus, the channel is available for reading or writing. Let's look at the syntax of channels. The channel type is defined by the keyword chan, and the data type is used to pass it. Channels can pass arbitrary data types and even other channels. Also, channels have to be allocated with the make function. Let's open an example from the previous video that runs 10 goroutines and see how can we synchronize the main goroutine with others using channels in order to avoid the sleep call, which is not the best design decision anyway. For that, we add another argument to the routine, which is a channel of ints, which will be used to send the integers to. Then, we will receive integers from that channel in the main goroutine and print them in a loop. A pretty simple example, though it demonstrates the concept. Note that we don't use sleep, but we receive data as it comes to the channel, and the application will finish operating after all data has come. You can run the application to see that everything operates just fine. Also, note that the channels have a pointer nature, and they are always passed by pointer. You cannot copy the channel in memory by passing it by value as plain data types or struct. Here, we used a yet unfamiliar operation less than minus. As you could have guessed, it serves as a send or receive operation for channels. If channel variables are on the left, we send data, otherwise we receive data. Also, note that we don't save the integer we receive from channel when calling the println function. Such an expression is also useful, like in our case. Our example is a classical usage of work-finished signaling. Go is very popular for writing command-line utilities. Such utilities often use goroutines in order to parallelize their execution by splitting tasks into different goroutines. These goroutines can receive a channel of booleans in order to send a value into it to signal that it finished its work. The signal is caught from the main goroutine, and it is very similar to our example. So, such kind of usage is an example of how channels can be used to control the execution flow of your application, along with sending actual data that has to be processed. In this video, we have discussed unbuffered channels. The next video will be devoted to buffered channels and their purpose in applications. In previous video, we were discussing channels and unbuffered channels in particular. Unbuffered means that they can store only one value at a time. This video is devoted to buffered channels. Buffered channels have that name because apart from behaving as channels, they have a buffer of items inside. It means that if you send data, the execution won't block unless the channel's buffer is full. The same goes for receiving. Receiving won't block the execution flow unless the channel is empty. While unbuffered channels are very useful for execution flow control by blocking goroutine execution until a signal comes, buffered channels are widely used for implementing data queues. The main advantage before ordinary queues is that they are guaranteed to grant synchronized access, and they guarantee that goroutines don't eat your CPU time when trying to receive data from empty queue or trying to add items to a full one. Let's move to the declaration. The way to create a buffered channel is pretty similar to ordinary channels, but we also add the second argument to make the function call telling us the size of the buffer. This way you can think of the unbuffered channel as a buffered channel with a zero-sized buffer. Let's see the example that shows that the receive and send operations do not block the execution. First, we send 10 integers to channel and then we read them. Everything happens consequently. Let's run an application and we will see that nothing is blocked and the application finishes successfully. As was said before, the buffered channels are good for implementing queues. The most interesting thing about queues is dispatching. You have to understand if the producer goroutine produces data fast enough to fill the queue. There are enough workers on the other side to process the data. This situation is exclusive for every case, so you cannot just guess. But what is good about channels is that if either workers or producers begin to block, the CPU time is not consumed. So you can just monitor the behavior and tune the number of workers. Let's look at the screen to see the implemented queue, just to demonstrate the concept. Here our routine function starts at the beginning by reading from the in channel. It blocks until the recipient receives some data as the channel is empty. Then, in the main goroutine, we send the data. When the channel fills, the sending operation blocks and the switch to goroutine is performed, and sums begin to calculate on received values. Also, note the OK notation when receiving data from channel, and the close function at the end of the main. The close function is used to close channels. It means that the error will happen when we try to send something into a closed channel. Also, just receiving the data will cause receiving zeros all the time, and the for loop will hang forever. So we add a conditional break to avoid this situation. The OK variable will return 0 if we try to read from a closed channel. And the out control channel is used to signal that all the processing was finished in order to prevent the main function from finishing before time. This example is more complex but demonstrates almost all capabilities and powers of channels. And the last kind of channels we are going to discuss is unidirectional or one-way channels. It can happen that you accidentally send data into the channel when you have to receive it or vice versa. This is what a one-way channel declaration is used for. It signals the compiler that only receiving or sending can be performed from such channels. Let's change our routine header to demonstrate that. We have just added a receive operation before the chan keyword because in our function we are only going to receive data from a channel. Let's apply the same for the out channel, but restrict it to send only. In this case, we put the send operation after the chan keyword. Let's run the application to see whether everything works just fine. At this point, we have finished discussing channels and their features. Now you have to be able to operate channels and build more complex solutions based on the knowledge received. In the next two videos, we are going to discuss the most popular patterns of channels usage. In last videos, we were discussing goroutines and how are they used in order to add concurrency and parallel execution of code to our applications. This video is devoted to fan-in pattern, a typical way to solve the problem of gathering data from different sources. As we've discussed before, channels are the best way to organize a data flow between goroutines. Sometimes it happens that you have several sources that produce data. As we are talking about the Go language, we will also consider that they send the data into channels. If you have different sources of data, you could save the data into temporary regions and read that data in separate goroutines in order to continue processing. But in the Go language, channels is a preferable way of doing all sorts of communications. A fan-in pattern is a way of streaming data from different sources into another channel. You can think of it as manholes. When it rains, all water streams running down the streets are gathered through manholes to soil pipes and then out of the town through a soil pipe. The same principle lies behind the fan-in pattern. You take all the data coming from several channels and pass it into another third channel in order to pass it for further processing. It simplifies future processing as everything will happen in one place. The best way to implement a fan-in pattern is a select statement that we have not used before. A select statement is very similar to switch, but it works with channels. Let's look on the screen and see how the fan-in pattern can be implemented using select. First of all, note that our fan-in function returns a channel. Such kind of functions are called generators. You then read from the return channel and the goroutine inside fan-in generates data. As you see, we use the infinite cycle and select inside it. The select option works by reading from the first one available for a reading channel. If there are more than one of such, it reads from the random one. In case of the fan-in function, the data will be received from ch1 and ch2 channels and sent to out channel, which is then used in the main function through the manhole variable. You can also mention the time after function. It is a special function that returns a channel which will be available for receiving data after the time specified is passed, 2 seconds in our case. As we didn't implement producers for ch1 and ch2, the application finishes execution. This is what we have about the fan-in pattern. You can play with the code in order to write generators for those channels, but our task here is to look through the concept. In the next video, we will talk about a kind of opposite task, a fan-out pattern. In the previous video, we have discussed how data from different sources can be combined into one stream using the fan-in pattern. In that solution, we have made a separate generator function that returned a channel for us, and that channel is quite usable for getting data in order to process it. In software engineering, distributing data between workers is a typical task. You will find a lot of dedicated general-purpose software that solves this task, while it can easily be solved with Go. Let's explain what the problem is. Consider a stream of data that must be processed somehow. It is much better to be processed concurrently, so the application could deal with several tasks at a time instead of reading data and processing it consequently. Those functions that do the actual processing are called workers. Workers receive data from a single queue. The main problem here is asynchronization, but channels do these jobs by design, so we can easily perform this with a fan-out pattern. Actually, we have a powerful codebase for this. We have implemented a simple queue in the third video of the current section, so let's return to that code once more. Here we have a queue and the data is processed by one goroutine, but no one can force us not to use more than one, so let's create 3 goroutines. Note that they still use the same channels. The input channel is synchronized, and it means that none of the worker functions can receive the same data more than once, so the code is safe. But they also use the out channel to send the finished signals. So the condition of the execution of finish will be receiving of the 3 booleans through that channel. Let's make the change and run the application. As you can see, several goroutines still run fine and produce the desired calculations result. At this point, we have discussed all means that Go offers for the concurrent execution of code. We have discussed goroutines and its scheduler, synchronization primitives and channels, and the most popular patterns of channels usage. Actually, we have finished discussion of all features and possibilities that are required for beginning your application development in Go. So now we are ready to proceed to next sections where we will be creating real-world, useful working web application. This application will help us gather all the knowledge together in order to see a working product. Let me introduce you to the 7th section of the Building Your First Application with Go, in which we will start to actually build a full application that will be finished in the end of the last section. In this section, we will start to build a web-based application, and everything you need is a Golang compiler, a text editor, and your favorite web browser. So let's start with the definition of a web application. A web application is an application that responds to user requests via the HTTP protocol. Most of the data processing is done on a web server, and the client just receives the results of calculation, usually as HTML formatted documents. Fortunately, you don't have to do much to run your own web server in Go. There's a net/http package in the Go standard library that provides a basic framework for running a web application, including a web server. It deals with all network communications for you and knows how to send responses and process HTTP requests. All you have to do is to code your application logic. Everything else is done for you. So let's look at the design of the simplest Hello World web application. This Hello World is different from the one we wrote in the first section. Here we will accept HTTP requests as input data and will return HTTP response as data processing result. First, we import the net/http package, which provides support for web application specific functions and types. Then we make a structure of our application by adding functions called handlers. In our case, we have only one handler, which is responsible for showing the Hello World web page at the root of our website. And the last thing to do is to start a web server. In our case, it is done with the http.listenandserve function. It accepts the host and port to listen to incoming network requests, and a handler, which is responsible for translating a URL path to a corresponding handler, which is invoked when a client visits that path from browser. This is how the simplest web server looks like. Let's run the application and open it in our browser. Here you can see our Hello World page, which the root handler function is responsible for. Now about the web application anatomy. It consists of a web server which is created and started by the listenandserve function. Actually, listenandserve is a shortcut for making new http.server structure and running its HTTP server method. A web server is responsible for all network communications and HTTP protocol handling. The next part is a multiplexer. We used nil to choose the default one, default serve max. This component is responsible for mapping a URL path into the appropriate handler function. The next part is a set of handler functions that implement logic of our applications. These are mandatory parts, but developers usually also use one more important part, templating system, a component that implements templates for your application. Remember formatting from the FMT package? It is similar, but usually more complicated. At this point, I would like to greet you with the first working web application written in the Go language. Now we are ready to move on to see how we can process requests in order to work with the user input in web programming. So, we are done with the web server. We have learned about this in the previous video. In this video, we are going to talk about multiplexers and handlers. The work that a multiplexer performs is usually called routing, a process of mapping URL paths into appropriate handlers. In our Hello World application, we had only one handler. In our application, we used default serve max, a default implementation of multiplexer, which does not support variable values but only plain paths. It means that if you want to add some variable value into your path, you cannot do that. You operate only hard-coded strings. Let's add one more handler that outputs one more page called hello name. Remember, you cannot substitute the part of a path with a name string for now. It is not possible with the default multiplexer. But we still have another common way to receive input parameters in a web application called a query string. Query string starts at the end of the path with a question mark symbol, followed by name-value pairs splitted with ampersands. The name and value are splitted with the equality sign. You can get access to query string inside the handler function using requestFormValue method. Let's make our new handler customized by users, letting them choose the hello phrase and name. Now we can run our application and enter parameters in query string. Let's make a French greeting by inputting hello equals bonjour and name equals Johnny and press enter to visit that URL. As you can see, our hello world has now changed its face into bonjour Johnny. You can also play with other values. There are also situations when you would like to pass several values with one name. It's a way to send a list of values at the application's input. Then form value is not enough because it will only return the first passed value. You have to use parseFormRequest method and then use the request.form field to receive all values. Another way to receive an input is a multiplexer. While the default multiplexer gives you very basic functions, there are a lot of third-party open-source projects that implement sophisticated templated multiplexers based on different types of syntax. The one I use for my everyday work is Gorilla/Max. It is a part of the Gorilla Web Tools package whose homepage can be found at http://gorillattoolkit.org. And the charm is in the fact that you are not forced to use the whole framework. You can just take one component and use it. I will remind you that you can use the go-get-github.com/gorilla/max command in order to get the Gorilla/Max package installed on your machine. Let's look at the example of our application but with the Gorilla/Max multiplexer. We will also receive parameters via the URL path instead of the query string. As you can see, the code is very similar, except that we have used the max.vars function to parse path variables. Let's run and see how our URL looks like. Modern web developers prefer customizing via paths instead of a query string. Such an approach is more appropriate and is loved by SEO specialists. At this point, we are done with processing input via the multiplexer and query strings, and we are ready to move on to see what are templates and how do they simplify web development. In the previous video, we were talking about processing user input in a web application. The previous two videos are good enough material for developing web applications. But web applications and websites in particular contain large web pages that consist of a lot of content, columns, text, banners, and so on, and it's quite hard to get everything written to response writer in formatted strings. That is why developers all over the world use templates. Templates are parameterized texts that are usually kept in text files on your server. Parameterized means that you define placeholders in the text of your template, which are filled for each request depending on incoming parameters from users' requests. Go language offers the standard library tool located inside the HTML/template package that implements simple templates logic. As with multiplexers, HTML/template supplies only basic templating logic, such as placeholders for strings and security. By security, we mean strings escaping, which makes your application safe from text injection. Text injection is a widespread type of attack. By manipulating request parameters, an attacker can inject malicious JavaScript code in your application page that can affect your application users. Let's see how templates can be added to your application and used in your work. First of all, we need to import the HTML/template package. Then we create a new template and pass a name to it. Then we need to create context and render the context into a template. A context is a parameterization of your template. Let's create a template as a string. Do not worry, template package also allows loading templates from files. Here we have two placeholders, one for hello phrase and one for name. We create new structures encapsulating both fields in order to use it as our context. In our handler, we use multiplexer variables for input and build context out of them. Then we parse the template and render it. Let's run an application to see the results. And here we are. The results are pretty the same. Another cool thing about templates is that they can be pre-parsed. You can factor out template creation and phrase it into the init function of your module, for example, and your template will be parsed only once and then applied for each request. For a large template, it will save you a lot of CPU cycles. As you could see, the template syntax is quite simple. We use double curly braces to define which structure field to use after a dot. You can also use a single value as a context for a template. Then you just put dot inside double curly braces and that's all. Fairly simple. There are also third-party templating languages which are more complex and powerful that implement features such as cycles and conditional execution of template parts. And the last powerful feature templates usually have, a template inheritance. It works by defining blocks inside templates which can be redefined in child templates afterwards. It is useful because most websites have a similar page structure and a lot of blocks are repeated from page to page. Well, that's all for templates, and we are ready to move to the next video. In previous video we were discussing templates. While we used templates as a bytes array, which was directly present in our code, usually templates are loaded from files. This decision is wise as developers, namely backend developers, are not only ones who work on templates. Templates are usually made by web designers and front-end developers who may be not familiar with backend programming language, Go in our case. So where is the problem? Every time we load a file from hard disk, a system call is made, which slows down your application a lot. Template cache is usually used to preload templates and save them in memory so that they can render context in future. Writing your own template cache is the first way you can think about template caching. The simplest cache is usually based on making a mapping of templates names as strings to templates. But fortunately, Go offers template caching inside its HTML/template package from the standard library. The easiest way is to use the must function from the package. It takes all past templates and parses it into a single template object. After that, the executeTemplate method is used to execute templates by the given name. If you load templates from files, for example with the parseFiles method of the template structure, the template names are named after the file names they were loaded from. Let's see an example of template cache based on our previous example. Here we move template loading into a separate function and call this function inside the init function of the module. Then we rewrite handlers in order to make templates rendering called from the object received to the must function call. We also create text files called hello.html and root.html in the same folder where our application module resides. Let's run it and see whether the result is the same. So this is how easily the template caching can be implemented. Another popular thing about templates is templates invalidation. It is very convenient for templates to not be cached during development, so you can edit your templates without having to restart the web server. The solution depends on how you implemented your template cache, so it is good if you think of it before adding the cache to your application. That's all for the template cache. Template cache can really boost up your application, especially if you have a lot of templates in use, so consider it every time you begin creating your website. All throughout previous videos of this section, we have familiarized ourselves with all the basic technologies used in web development, including web server, routing, and templates. The last video is devoted to error processing. In previous sections, we were talking about errors, and we were discussing only one type of error, which is predefined by functions and processed as function return values. These errors are simply objects that conform the error interface. The interface consists of only one method, called error, that returns a string that is an error description. So basically, every object that implements that method can be treated as error. There is also another kind of error that happen in runtime called panics in Go. Panics happen in situations where errors cannot be processed, like in previous case of errors. Panics happen when errors are unrecoverable. Such errors have to be caught. Catching panics is another way to implement error processing in your application. You have to remember that panic immediately breaks goroutine. You can also call panic built-in function manually in order to cause a panic inside the function. Though it is possible, it is discouraged in Go to use panic recover in favor of errors, which we were talking about in the previous sections. While it is okay to use panic recover mechanism internally in a package or a library, it still must expose its public API through errors, not panics. Let's look at the situation when a panic happens, division by zero. Here we have a function that can produce division by zero panic. Let's call it with appropriate arguments and run the application. You can see a traceback and our application crashed. Division by zero is an example of an unrecoverable error, but if it happens inside the goroutine, it can be caught at an upper level in a caller goroutine. Go offers a way to catch panics with the recover built-in function. You can call the recover built-in function as a deferred function in order to check if panics happened. Recover stops application panicking and returns an error if it has happened or nil if there was no panic. Let's add a defer function call that catches panic inside the main function and just print out the error that recover produces for us. Here it is. Now our application has not crashed. We received just an error that we already know how to process, and we can make some decision in order to make our application move back into its normal state. Division by zero is a kind of panic that is connected with your CPU operation, so it's a machine error, but you can also generate panics yourself. If you don't like propagating errors through a chain of goroutines, you can make some goroutine panic by calling the built-in panic function that receives only one string parameter, an error produced. Panic will spread up through the goroutine callers chain till it encounters the recover function that stops application panicking. This is all for advanced error processing. At this point, we finish our 7th section of the Building the First Application with Google Go video course, and we are moving to the last section in which we will finish our image manipulation application. In the last section, we will try to remember everything we have learned before in order to make a nice, useful, production-ready application. See you in the next section. Let me introduce you to the last section of Building your First Application with Go video course. So far, we have finished learning features of the language that make up a strong basis for a software developer. In this section, we will finish up the creation of the web image manipulation program. In the previous section, we have discussed web applications. Now we are going to add logic to them. As we have mentioned, all business logic of the application started inside handlers that process the user's input. As we are doing the image manipulation program, the first thing we would like to do is image uploading. Image uploading is done via the HTML form. We won't go deep into the specifics of HTTP protocol, but will concentrate on issues at the server. So let's make a simple form with the file selection field and upload button. The form passes the image along with request via the post request type, while in the previous section we were using the get request types. Also, we specify the encoding type to be multipart, so the web server is aware that we're sending something along with the request information. At the server part, we first need to read the file coming from the client. For simplicity, we will only support JPEG images. Decode an image to get a matrix of pixels to work with in future, and save the image in the main memory of the application to operate its data. In order to achieve that, we create a main page of our application handled by handle_root. It just produces a web page with the upload form, and then we create a handler that receives data and saves it in memory, called handle_upload. Fortunately, as you can see at the screen, Go language offers a straightforward API for all that was said earlier. Notice the last line of the handle_upload function. It is used to redirect the user to some other page usually received from the server with the HTTP GET method. Here we redirect the user to a page where an uploaded image is rendered. So the last thing we need here is to make that page, and hence we add one more handler for that. Here all we do is the opposite of what we did with the upload step. We take an image from the memory, encode it into the JPEG format, and write raw bytes into response writer. All other source code has to be familiar for you for now. Let's run an application and try to upload an image to the server. As you can see, everything works just fine and at lightning speed. Well, if your image is quite big and your application is on the server far away, you'll have to wait a bit. A small but victory. This video taught us how to upload images to a server and how to show them to users. Now we are ready to move on to manipulate them a bit. I mean pictures, of course. In the previous video, we have made some input-output logic for our application. Now we are ready to do the most interesting part, that is, process images. Go offers the standard image package and sub-packages that do the job. As was said earlier, images are represented by matrices of pixels, though internal implementation of pixel matrices can be different in different packages. First of all, let's improve our code from the previous video and add an editor page which will contain an image inside, not just an image as a stream of bytes. There, we place a link by clicking on which the inversion will be done. Let's look at the inversion handler that does processing. First, we create a new RGBA object. It is used to manipulate pixels. We need this additional object because image itself is read-only. Each pixel holds a color value consisting of 4 components: red, green, blue, and an alpha storing transparency. For manipulating colors, we import the additional image/color package. The algorithm is pretty simple. We iterate through all pixels from the original image and write the corresponding ones to the RGBA object. Corresponding pixels have different colors, which are calculated as follows. Each component of a color equals to 255 minus the original component. We leave the alpha value untouched. The last thing we do is receiving the image object from RGBA with sub-image method. An argument specifies a rectangle corresponding to the bounds of the image we are taking. Then we save the new image back and make a redirect to the editor page. Let's run the application and try out new feature. Well, it works as a charm. Now our application is useful. Remember that Go does parallel execution of code very well. If you have a quad-core processor, it would be wise to make our algorithm parallel. Let's consider this a home task in order to improve the application's performance. You won't need any synchronization of data access because every portion of information is processed independently. The simplest way is to split an image into several parts on y-axis and run nested cycles in goroutines. Other solutions are also applicable. Very well for now. We have written a first really useful application. For example, I often use inversion when I process screenshots of terminals which are usually black with white text on them. Color inversion helps me save a lot of ink while printing. Well, that's all for inversion. Let's move forward and add one more function to our application: clockwise rotation. In the previous video, we have learned how to perform image processing. The current video is also devoted to image processing and to image rotation in particular. While rotation algorithms are very complex, we will restrict ourselves to rotations to 90 degrees clockwise. This will seriously simplify our algorithm. Let's look again at what is implemented in our application for now. As was said, we use temporary storage for processing images. First, we have the read-only image instance, and then we have the RGBA instance, which we can use for manipulating pixels. While such an organization seems strange, if you check different algorithms, you will see that most of them need original pixel information along with modified ones, so modifying the image in a place is almost unnecessary. On the other hand, when you get an image instance from the RGBA instance via the subImage method, you can reuse RGBA object's pixel storage. For rotation, we create a new handler as usual. Its workflow is the same as in case of inversion. The difference begins when we create a new RGBA object. First, we create a new rectangle, which in this case has swapped dimensions. Height is swapped with width. The algorithm is pretty simple in itself, and an event takes less space than inversion, though it can take a bit to think how to implement the clockwise inversion. Here's a set method call that does the job. If it's hard to get why such arguments were taken, it could be very appropriate to just draw two rectangles with a pen and paper and transfer some pixels manually. Everything else is pretty the same as before. We also modify the editor page handler in order to add new controls that will lead to the link handled by the handle rotation handler. Let's run an application and play with our new function. First, we upload an image, and then we can use our newly created feature of an application. Here, you can rotate and invert in any sequence you like, since features work in a pretty universal manner. That's all for rotation. Now, our application has two nice working features. But what about the source code? I mean the design. I would say it is horrible. I would like to remind you about everything that was learned in the previous sections. In our application, everything is mixed up. Let's move forward to the next video to see how we can refactor our code to improve it. In the end of the previous video, we have stated that our application needs a redesign. While the application works and is good enough for demonstrating concepts, it is unacceptable to push such code into production. So, what are the problems? The first is that HTML templates are mixed up with code, which makes the Go source hardly readable. The second, web application-related logic and image manipulating logic are glued together. Consider that you would like to reuse the rotation code somewhere else in the application, then you will have to copy-paste the existing code, which is a bad practice. Inversion and rotation handlers share a lot of code having a similar beginning and ending. Let's begin by moving the image processing logic into a sub-package called wimp/transform. We define three modules there. Transform for making a registry of transformers and exported functions to access it. Invert, which will implement the transformer interface and inversion logic, and rotate, which will implement the transformer interface and rotation logic. These two transformers are registered inside the init function of their modules. And here is the benefit. If you want to add an additional transformer, you just create a new object that implements the interface and register it. No previous code modification is needed, and your application is secured from regression bugs. The templates are a problem now. We move templates into separate HTML files, which now can be modified separately from the main code. Now we load all templates with one call to the template_must function and cache them in memory. Along with the benefit mentioned before, it's a pretty good optimization. The next we can do is a redesign of the HTTP API. Now our transformations are done through the same interfaces. So we can specify the name of a transformer from a client, get it by the name on the server, and just run it. The code is the same for both. So we eliminate handle invert and handle rotate in order to create one unified handle transform that receives a new parameter via the query string. And the last thing we need to discuss in this video is code-driven automated testing. Such kind of testing demands writing pieces of code that calls public interfaces of your application's components with predefined arguments and validates that the returned results are correct. Let's write a single test in order to illustrate those words. The first thing you need to do is create a new source code file whose name ends with _test.go. This ending is a signal to the Go tool to treat the source as a testing code. In that module, the standard testing package, which contains facilities for writing tests, has to be imported. In the Go language, a single test is a function whose name is exported and begins with test that receives a pointer to the testing.t structure. This function does not return anything. It uses the testing.t structure to tell if current test passed or failed. The body of the function just calls some code of your application and checks if the returned results are correct. For testing web applications, there is a special net/http/http test package that is capable of simulating client-server interaction without running the actual web server. Let's test if our root page works by making a fake request and testing the returned HTTP code, which in case of normal execution must be equal to 200. For that, we are going to use the http-test.responseRecorder object that implements the http.responseWriter interface. We can run tests using the go test command of the Go tool specifying the package to test, which is WIMP in our case. As you can see, the test does not fail anymore. Now look at the overall code. The main WIMP module contains only web application-related logic. The WIMP/transform package can now be reused in other projects and is absolutely independent. And the second, no HTML in Go modules. Templates are now in a separate folder and can be freely used by front-end developers. This looks more like a nice production-ready project than the previous variant. And this is the goal we have achieved. Let me start the last video of the Building Your First Application with Go video course. During this course, I have tried to lead you through the very basic concepts of software development to the creation of a production-ready web application. Why web application, you can ask? The answer is simple. You can develop and run such applications on any platform and operating system the Go compiler supports. It is basically OS-independent technology. We have started from downloading a compiler and ended up with a working web application, and that was the purpose. Let's look through a short list of what was learned. Go language memory structures, how to implement conditional execution of code, cycles, functions and packages, object-oriented development, and the distinctive core feature of the language, goroutines and concurrency programming. This list contains basic features of the language. The material we have discussed throughout the course make up a solid basis for you as a developer. And after finishing this course, right now, at this point, you have to be able to build applications. You will also have to explore much more about development in this language, and you will discover a lot of areas where the language can be used. Now, I think you would like to ask me where to go further, and I will try to answer this question. First of all, develop. Practice is everything. Try hard to apply newly received knowledge in practice making some project. The next, work with the Go language official site. There are a lot of materials for advanced developers, starting from an effective Go tutorial and ending up with language reference. Also, Go language has a very fast-growing community. People on forums and question-answer sites all over the internet will help you in minutes. You just need to ask. And the last, I would like to say many thanks to you, my dear viewer, for staying with me through the whole course from the beginning to the very end. I hope the lessons that were given during the course will help you to develop great applications.